Good evening to all. Let us start the session today on vertical earthquake. The vertical earthquake is the information any design engineer should have when they are designing the buildings. Here on the screen, you can see there are various types of vibrations that are mentioned. So welcome Subhash and welcome Binur. Today is an important topic that every engineer should know that we are discussing for earthquake. So what are the types of vibration that happen in the structure, right? So first is the extensional vibration. Extensional vibration, that means a spring is fixed on the top and the mass is suspended from bottom and it is free to observe a vibration in the vertical direction. So this is what happens under the vertical earthquake. That is the diagram number 1. So here you can say that extensional vibration, whatever has been shown, is the vertical earthquake phenomena that will happen on your structure when the vertical earthquake comes on your region, comes in your region. So building will undergo the vibration in the vertical direction. That's why it is called vertical earthquake. Now, what are the effects of vertical earthquake that we'll discuss? So first is the extensional vibration, that is the vertical earthquake. Second type of vibration is bending. So the structure is bending in positive direction, then in negative direction. So bending is the second type of vibration that happens. Third is the shearing. So buildings are generally tall buildings. Bending is critical, and for the low to mid-rise building, shear is critical. That's why for low to mid-rise building, the type of vibration we consider is the shearing type of vibration. And for tall buildings, we consider the bending type of vibration. And torsional vibration, it is common for all type of buildings. So what is the torsional stiffness of the building? Based on that, it will decide that first mode will be torsion or it will be translation. And if it is the torsional mode of vibration, then it will attack the structure in the weakest direction. So that is the four type of vibrations that we should know that are to be applied on each type of the structure. Whether my structure is a slender, so bending will occur. If it is a shear type action, then shearing will occur. If it is in the near to earthquake zone, then it will have the vertical vibration, and torsional vibration is common for all. So that is called the torsional stiffness that we consider. So for vertical direction, what is to be done, that we will see today. Okay. So here you can say that this I have shown you in ETABS that what is a match response spectrum. So this I have drawn that for zone 3, right, and zone 4 and zone 5. So we can create a time history from the response spectrum. So we'll define the response spectrum function in ETABS in the define section. Okay, so it will give the topmost figure. Let me just, yeah. So this figure we will get from definition of the response spectrum. And then we will give a match response spectrum for zone 3. Okay, so what we will do, we'll define a zone 3 function in ETABS. Then we will match it for the given time history in ETABS. So that time history will be matched with zone 3 function that we have defined. So we will get a time history that is matching the zone 3 with response reduction factor of 5. Okay, so this is the DBE level response spectrum that we had defined, and from that response spectrum we have got DBE level time history for zone 3. Similarly, when we define the response spectrum function for zone 4, zone 5, we can achieve the time history for zone 4 and zone 5. So without having any time history, we can generate a time history, and all these time histories are generated for r equal to 5. Okay, and if you give r equal to 1, similarly you can generate your particular time history for your type of structure. Okay, And here, as r equal to phi is given, and along with that, you know that z is zone factor. Okay, so zone factor of zone 3, 4, 5 will be mentioned here, and it will be divided by 2. So this history representing the R of your structure and Z by 2. That is why it is called a DBE level uh, uh, time history, because you have defined a DBE level function in your ETABS. So this is how you can generate your time history without having any time history. So you do not require an external time history from the defined response spectrum. You can generate your particular time history, and that you can use for time history analysis in ETAP software. Okay. Okay. I think if it is clear, we move forward. So this was the basic information that I had to share with you, that how we can convert the response spectrum into a time history, and that can be used for the analysis and design in ETAP software. Now, vertical earthquake, that is the topic. Let us start with that. Now, in as per the clause IS 1893/2016, so this is as per 2016 we are talking. So that depends on any code you take, American code or whatever code is there, but concept remains the same, only factors are changing. So effects due to vertical earthquake shaking shall be considered. Now, when it shall be considered, that is important. In all buildings, it is not to be considered. So in what cases it shall be considered, and why it shall be considered. So it shall be considered for stability of embankment, bridges and dams. So whenever you are dealing with the bridges, the mass is very heavy, and if the vibration takes place in the vertical direction, it will cause a lot of shear in the bridge piers and as well as in the girders. That is why vertical earthquake is very important for dams, bridges and embankments. For safety of buildings, embankment, bridges and dams or their components. Okay, so whatever the components are attached to the buildings, what are attached to the embankment, what are attached to the bridges and dams, all, and that also shall be checked for vertical earthquake. Okay, so what are the following cases in which this shall be done? So what type of structures it is to be done, and in what cases it is to be done? When the structure is located in seismic zone 4 or 5. So in that it is compulsory to consider vertical earthquake. Structure has vertical or plan irregularities. Okay, so we do not know that what will be the vibration in the structure in which there are plan irregularity and vertical irregularity, and hence we have to consider the extensional vibration of the building. And in such cases where irregularities are there, plan or vertical, you have to consider vertical earthquake. That is compulsory. When structure is rested on soft soil, so when the structure is resting on soft soil, then it is obvious that with the earthquake it will start moving, and the above ground structure will experience a vertical effect, and that's why we should consider vertical earthquake where there is a soft soil. Now, structure with long span. So this is very, very critical, that those structures that are of very long span. So what type of structures are long span? Bridges are long span, and in pre-stressed structures. So in pre-stressed structure, long span beams are provided. So that is in and the size of the pre-stressed beams are very small as compared to regular beams, and span is large. So what happens that whenever the vertical earthquake will come, it will experience a vibration in the vertical direction, and it will experience high amount of shear, and it may fail. So in large span or structures, uh, what will happen? The amplification of the oscillation will occur due to flexibility. So if the length is high, right? So what will happen that your structure will become more flexible, and whenever you apply a vertical force here, it is different. But when a vertical vibration will occur, then it will create, due to higher flexibility, the amplification will take place. So some delta displacement occurs in a static load case, but in dynamic condition, this will be amplified, right? So it will add the amplification factor. So in that case, whenever the large span structures are there, we should consider the vertical earthquake. Structure has large overhangs and of structural members or subsystem. Large overhangs in the sense you have balconies, right, in the building. So balconies are the overhang, one type of overhang. Second is your porch at the entrance of your building. Porch area is there. Balconies are there, porch is there, and on top of the building, right? So you have a overhead water tank on top of the building, or something is extending above your building. Or let's say it is a type of building in which high change in geometry is there. So this is what is happening. This is acting as a separate structure, and this is also acting as a structure on top. So they will have a larger flexibility under the vertical earthquake, and that is the reason we have to consider the horizontal acceleration. You know that horizontal acceleration and vertical acceleration we consider in these type of structures wherever the overhangs are there. So overhang can be vertical overhang or it can be a horizontal overhang. Horizontal overhang are balcony and porch, and vertical overhang are the overhead water tank or some geometry irregularities there in the building. So that is to be considered in vertical direction. So in that case, we have to consider the vertical earthquake. So whatever the projections are there in the building, for them we have to consider the vertical earthquake. So projection may be in horizontal direction or projection may be in the vertical direction. So those are called the sub-assemblages of the main building. So for main building, we are designing for vertical earthquake, as well as the assemblages that are connected to the main building or the main structure. For that also, we are designing separately. So we will separate this top structure from this building, okay, and we will apply the higher amount of the acceleration, considering it is a cantilever, and its members and its junctions will be designed for vertical earthquake. Okay, so for all projections, suppose it is in zone 3, so we don't have to consider vertical earthquake, but for projections we have to consider the vertical earthquake, and we will separate out this much region from the building and design only this much region for the amplification of the oscillation due to vertical earthquake. So we'll see how it is done. It is just to show you that we will separate out this if it is in zone 3 and zone 2. If it is zone 4 and 5, then entire building will be designed for vertical earthquake. And in zone 3 and 4, the sub-assemblages have to be separated and it has to be designed for vertical earthquake. So all cantilevers projections have to be taken out. That these are called the sub-assemblages. Building and sub-assemblages both need to be designed for the vertical earthquake. Now, pre-stressed structures and structures with pre-stressed members. So due to large span and its size is less, it will undergo vibration very easily. And that is the reason we are for pre-stressed structures, we have to consider the vertical earthquake. So these are the conditions in which the vertical earthquake shall be considered for design of the buildings and its sub-assemblages. Now, as per the code, what should be the vertical earthquake for buildings? So part 1 is for buildings. Okay, so we are considering right now the buildings only. So it is 2 by 3 of Z by 2 and I by R. And 2.5 is SA by G. Okay. So many have confusion that why this factor is multiplied by 9.81 because it is SA by G. So when we are considering spectral acceleration only, then obviously we have to multiply by G. Otherwise, we will get SA by G only. So it is divided by G right now. If we want spectral acceleration, then we have to multiply it by G to get the acceleration, right? So if you want the acceleration value, multiply by G, or if you want normalized AV, then you take whatever the code has given to you like this, right? So in the define function of ETAPS, you have one definition of the function and another is the load case definition. In load case definition, you have a G factor. So in ETAPS, in load case, you will get G, it will be multiplied and converted into acceleration. So what you have to define? You have to define is 2 by 3, Z by 2, 2.5 divided by R by I. So if your R is 5, I is 1 or 1.2 zone factor, so that will be a constant line. So this will be a graph and this will be your acceleration graph. So for horizontal acceleration, it was like this, right? For vertical acceleration, it will be a straight graph. Okay, all values will be same because a zone is constant, R and I are constant, and SA by G is constant. So everything is constant. So your line will start from the value that you get from your input, and it will remain constant entirely for the given time period 0 to let's say 4 or 6 seconds, whatever the time period is there. So for that, it will be a flat response spectrum. So AV is flat response spectrum, and this is AH. This is horizontal response spectrum given in the code. Clear? So these are the two response spectrums when we are considering the vertical earthquake. So you have to define both in ETAPS. So in ETAPS, you will have to define the two type of response spectrum functions. And similarly, so response spectrum function and response spectrum load cases both need to be defined in ETAPS when we are dealing with vertical earthquake. So this is important in terms of definition of the vertical earthquake function and the load case. Now, when both horizontal, so in what case the code says we should use the vertical earthquake? So there are non-parallel systems, okay, non-parallel, or you can say non-orthogonal. So non-parallel or non-orthogonal system means your shear wall is not oriented in X and Y direction, it is in between. So let's say your shear wall is inclined right now, or your building plan is there in which the shear wall is inclined. So it is neither in X, neither in Y. That's why it is called non-parallel plan system. So when there is non-parallel or non-orthogonal, orthogonal means 0 or 90 degree. If your lateral load resisting system is uh, not in 0 degree nor in 90 degree, it is in between, then we have to consider the earthquake force in X and Y direction both. Okay, so in that case, you have to consider 100% in X and 30% in Y. Similarly, 100% in Y and 30% in X. So this is the condition in which we consider X and Y both direction earthquake. So this is called 2D earthquake, right? Two directional earthquake we are considering for this type of system. So when both horizontal and vertical seismic forces are taken into account. So previously we mentioned that in what cases you have to consider the vertical earthquake. So if that is your governing case, then you have to add the vertical earthquake also. So here you can see earthquake in X, 30% earthquake in Y, and 30% earthquake in Z. 100% earthquake in Z will never occur. Okay. So this is the load combination because we are always talking about plant direction, X direction and Y direction. Earthquake is always in X and Y. For vertical, we are adding the component of 0.3 of Z. Clear? So this is what 3D earthquake condition, three directional earthquake. Okay, so this is the three directional earthquake that we are currently seeing here. So this load combination has been mentioned in clause 6.3.3 of the IS code. And similarly in American code also, there may be a different condition. In steel code, there is a different load combination. In concrete design, there is a different load combination. So a combination may be any. Only thing is logic is that if the system is non-parallel, non-orthogonal, we consider 2D X and Y. And if the your building condition as such, you have to consider the vertical earthquake, then we consider three directional earthquake condition that is X plus Y plus Z. So plus or minus 30% Y plus or minus 30% Z. So this is for earthquake that is happening in the X direction. Similarly, 100% in Y, 30% in X, and 30% in Z, plus and minus. So all these load cases you have to add, okay, whenever we are doing the vertical earthquake. So how it will happen? It will not happen directly because you have defined earthquake X and you have defined earthquake Y in your load patterns in ETAP software. You have not defined earthquake in Z direction. So how will this vertical earthquake combination will come into picture? So whenever you will define a particular load case in your load case definition, okay, so load pattern, you will define only X and Y. So in load case, you will define the vertical earthquake. Now this combination you have to manually enter. Okay, so whenever you have to consider the vertical earthquake, you have to manually enter that particular load combination. Okay, so that also we will see. And this is earthquake 1.5 times earthquake X 30%, 30%, 1.5 uh, Y and 30% X, 30% Z. And similarly, this is how it is getting repeated every time. So plus or minus. So you can count. This is a one load case. Okay. So in this one load case, there is plus and minus here. Okay. So it is like two load cases generated for this. And again, it is plus and minus, plus and minus. So if it is plus, then it is plus and plus. Again, it is minus, it will be minus, minus. So I have a doubt that when it is written plus or minus outside, that automatically means that everything will be minus. So why it is written as plus and minus? So either it is a two cases or it may become 2 plus 2 plus 2, 6 cases it can become for your load combination. So based on that, you have to apply. But IS code says plus or minus, plus or minus, plus or minus. We generally create two load cases here of only plus and minus. We neglect inside plus and minus. So 2 and 2 4 and 2 6 and 2 8 and 4 12. So these 12 load cases at least shall be defined in your ETAP software. Clear? So this is your load combinations with the vertical earthquake that have been mentioned. So this is called the three directional earthquake that we are considering for our building. Okay, so once we are we have understood that in which type of cases the vertical earthquake is required and how it is defined and what load cases are to be defined, we can move forward. And here, importantly, right? So whenever we are defining a response spectrum function, okay, then we are giving it a scale factor. So this comes in under the design stage. So to design the structure, we are giving the scale factor and we are scaling to the static ratio. Okay, so we have defined in X direction. So this has the scaling done in X direction. This is the scaling done in Y direction. So what is the multiplication factor for vertical earthquake? So whenever you will be defining the response spectrum function for vertical earthquake, you will have a scale factor to define in the load case. Okay, so that scale factor will be is called the multiplication factor here. So already scale factor is given G. It will be mentioned in your ETAP software. In that we have to multiply a multiplication factor, right? And this multiplication factor will be what? The maximum of scaling done in X direction and maximum of scaling done in Y direction. So that ratio you find out and what is the maximum in X and Y that you multiply with G in the scale factor. So that is how your load case for AB will be defined in the response spectrum load case. So RSM V, whenever you will define RSM V, that is the response spectrum function in vertical direction, you will give a scale factor. Already it is given by the software G. This multiplication factor you have to enter based on your scaling done in X direction and scaling done in Y direction. What is the maximum that you have to multiply? So that will give your load case response spectrum function in vertical direction. So I hope this is clear till now that what is the procedure to do that as per the IS code. And as per tall building code in India, okay, so I think it is similar to the American code that vertical shaking shall be considered simultaneously with horizontal shaking for tall buildings in seismic zone 5. So what does this mean? That vertical shaking shall be considered simultaneously with horizontal shaking. So anybody can explain? What does simultaneously mean?
Happen together, sir.
Yeah, but how to define it?
In the load combination, sir, the 30%.
Yeah, that we are already doing. Then why 16700 is saying that?
Mm.
So what is happening? Whenever you are defining your response spectrum in X, okay, now it will be XV, that is two response spectrum, that is for X also and for V also you will define in your response spectrum load case. Similarly, RSM Y we consider, right? So Y plus V. So both two response spectrum will be defined in X and Y direction. So separate vertical response spectrum we may create, but it may, so what will happen? All your vibrations, dynamics will be considered using the vertical and horizontal earthquake. So for tall buildings, we have to give two response spectrum functions, okay, in X and Y direction. So clear, right now we are giving only X and we are giving only Y. So earthquake X, earthquake Y. Now earthquake X plus vertical earthquake function, earthquake Y plus vertical function. So this is how your response spectrum load case will change for tall buildings. So simultaneously it will occur. Yeah, so load combinations are already there, but for the oscillations we are considering to be same. So it will give you higher amount of oscillation and higher shear will get developed in your building, and for that you need to design your structure. Okay. So this is what is the difference between tall building and a low to mid-rise building, up to 50 meter and up to 250 meter, or let's say more than that. So this is how it is mentioned. So this is the response spectrum, right? I have defined in ETABS, or I have created it in Excel sheet right now. Okay, so this Excel sheet, whatever the SA by G versus time period was given in the IS code, that I have defined. So it is 2.5, that is the maximum value. Okay, and this 2.5 is what? SA by G that I have defined. Now what remains is 2 by 3, okay, and Z by 2 divided by R by I. So this factor I have not included here. So this graph does not have these factors. So these factors need to be added in my particular graph so that I can use it for the vertical acceleration definition in ETAP software. So the response spectrum function for vertical earthquake shall be taken as 2.5. Okay. User defined features for this Z by 2 R by I is already considered by the software. That is scale factor is now G. Okay. So what I have to do, right? So RSM, response spectrum method, vertical scale factor. Okay, this is the scale factor that I'm talking. So scale factor is what? Maximum scale factor of RSMX and RSMY, that is G. Okay, so already it will be there in your ETAP software. So what is there? I will be defining 2.5 and rest. This is your scale factor. This is what I want to say. So this is your scale factor and this is a 2.5 response spectrum. Why it is 2.5 only? Because it is the user defined. You do not, this ETAPS does not have this user defined response spectrum function. Okay, so default response spectrum function of the code is what is mentioned in the code, that is the horizontal acceleration. This I have to give by myself, user defined only. So I will give 2.5 everything. So 2.5 is defined. Now the scale factor will cover all these parts. So G is already there in ETAPS, G multiply by scale factor. So this will be my scale factor that has to be entered in your this response spectrum vertical load case. Okay, so whenever you are doing response factor on vertical load case, this scale factor you have to enter, and this is the function that you have to define. So this is the function to be defined, and this is the scale factor to be given for the particular load case. Is it clear? So if it is clear, then we can move forward.
Excuse me, sir.
Yeah,
This is the initial scale factor, yes, sir, for vertical.
yeah, initial scale factor.
Uh,
So see,
this is,
don't confuse between scale factor and multiplication factor. So scale factor, I right now told you. Multiplication factor is what will happen once you find the maximum scaling in x and y direction, right? So multiplication factor is yet to be multiplied here. So this is the initial, or we can say a scale factor, and next is the multiplication factor. So that will help you every time to define this response spectrum function. So scale factor we have defined. So this is the original uh, response spectrum of in the vertical direction we are considering. Now, when we want to scale it to the static Bayesian, then multiplication factor will be again multiplied, right? So that is what you are asking, Alec.
yes, sir.
Okay, okay. So here, right now, we have given the scale factor. Now, what will happen that once we will do the scaling in for static Bayesian, okay, for static Bayesian also, we will be doing it in the x direction. So VB static upon VB dynamic. Okay, so that we will get some factor we will get, and in y direction also VB static upon VB dynamic. So what will be the maximum of the two? That will be the multiplication factor, and that again we will multiply with the response spectrum this load case. Okay, so it will be like scale factor is there in E types, so it will be G already available into scale factor of 2 by 3, Z by 2, R by R, and into multiplication factor. So these three things will be there in your scale factor uh, when you are defining your response spectrum load case. So this is the final thing that you need to enter in the scale factor of ETABS tab. Okay, hope it is clear now that G is already there, scale factor 2 by 3, Z by 2, R by R, and multiplication factor is the scale factor of X direction and Y direction. Okay, so moving ahead. So what I have done, I have created this table, right? So what is this table basically? It is basically your scale factor. Okay, so scale factor is the factor z by 2, 2 by 3 into r by I, right? So here it is what? Zone 2, so it is 0.1 G, so z is already there. Zone 3, zone 4, zone 5. So your z value is obtained from here. Your I may be 1, 1.2 and 1.5, so I also have given. So it is 2 by 3 into z by 2, again I write, upon r by I. Now, SMRF means R equal to 5, okay, and OMRF means R equal to 3. So if your R equal to 5 is there, R equal to 3 is there, then this table I have created. And this will represent your scale factor. So directly from table, you can enter the scale factor. Okay, so this is how I have generated this table. So Z by 2, R by I, 2 by 3 in Excel, you can do this. So scale, so this will save your time. That is the only thing I have created it. So building structures identified as sensitive to vertical acceleration. Okay. So from US, I have got this paper of Dr. S.K. Ghosh. And what he is saying that horizontal or nearly horizontal members that are spanning 20 meter or more. So IS code is saying long span. So what is long span? 20 meter or more. So in that structures, vertical acceleration will be sensitive. This structure will be sensitive to the vertical acceleration. Horizontal or nearly horizontal cantilever components that are more than 5 meters. So they are saying that projections, but what is the length? IS code is not mentioning. So for 1 meter, should we do the vertical earthquake or not? For 2 meters, should we do the vertical earthquake or not? So that is not defined by the IS code. So this is the general definition by the practitioners and the researcher that they have mentioned, that horizontal or nearly horizontal cantilever components that are longer than 5 meters are sensitive to vertical earthquake. Horizontal or nearly horizontal pre-stressed components. So all pre-stressed components are sensitive to vertical earthquake. So building components excluding foundations in which demands due to gravity load exceed a high percent of the nominal strength of the component. So that are shear critical. So whatever the components are of lesser depth and are shear critical, okay, so all that will have a higher oscillation under the vertical earthquake, and that should be included as the sensitive to vertical acceleration. Vertical elements of the gravity force resisting system that are discontinuous. Okay, so what does it mean? What is a discontinuous system? The vertical elements of the gravity force resisting system that are discontinuous. So suppose a column is there and it is discontinued at bottom, and what will happen? It is created a cantilever portion here. So this will undergo extensional vibration due to because of discontinuity, and in such case this becomes sensitive to vertical acceleration, and this is the reason we have to consider vertical earthquake for such structures. Yeah, so wherever there is discontinuity, it will have higher vibration. So load is coming from top and it is vibrating uh, up and down. So it is an extensional vibration. Base isolated structures, it is compulsory to consider vertical earthquake because in vertical direction, the absorption is not there. So the structure will undergo the vertical vibration, even though horizontal is not experienced. So for base isolated structures also, vertical acceleration has to be considered. So what will happen? So effect of vertical earthquake on the RC structures, excessive overstress, compressive overstress, or tension failure that can occur in your columns on the ground story to first story. Okay. The vertical response can lead to failure for the ultimate states of flexure moment and shear. So moment and shear, both type of failure can occur in your structure. The shear may explain observed failure perhaps associated with underlying vertical motion effects because the compression can be reduced. So basically your shear resistance reduces in vertical earthquake. That is what is the bottom line, that shear resistance is reducing in the vertical earthquake. So moment capacity and ductility, very important, that moment capacity and ductility of RC columns can get reduced, and the failure is observed in the ground story and the first story. So you have to check the columns in the ground story and first story for the vertical earthquake, and mostly the failure may occur on ground story. So they have to be increased in size and reinforcement to consider the reduction in the moment capacity and ductility. Unconsidered fluctuation in the axial force due to vertical motions may predict flexural failure. So in columns you have PMM interaction curve, right? So when the P will increase, your moment will reduce, right? So moment carrying capacity of your column will reduce. So what will happen? This is your building, or let's say this is one column here, and some lateral force is acting, and now the vertical force is also acting. So due to higher amount of the axial force, its capacity to carry the lateral force reduces, right? So it will become negative. So what is happening? The moment carrying capacity due to application of higher amount of the vertical force. So either the column can become in tension in one case, right? Or it can become compression in the other case. So due to this, the capacity of the column gets reduced to carry the bending moment. So due to the lateral force, the bending moment it was carrying, now that carrying capacity gets reduced for the lateral forces. So that is the effect of the vertical earthquake on your columns. And it is always suggested to use shear wall in seismic zone 4 and 5. That is the reason. It has been observed that vertical ground motion can equal or even significantly exceed the local horizontal ground motion. So your AV can become greater than AH in low period range. So if your earthquake is a low earthquake also, so you have a low period range, that means in the acceleration region. Okay, so in acceleration region or in the low period region, what will happen? AV vertical earthquake can become higher than the horizontal earthquake because of the near source effect. Okay, so severe earthquakes in near source, it can have a vertical effect higher than the horizontal effect. And due to that, the capacity of the sections will reduce, ductility of the structure will reduce, and the structure may collapse due to this reason. So if that condition is not considered, then your structure will fail drastically. So this is the best explanation. You can say that this is the mass, right? And this is your column. It is going vibration up and down. And this is your earth and this is your building. Okay, so what is happening? Earthquake, vertical earthquake, P waves are sensitive. As the P wave typically associated with vertical earthquake motion, as a higher frequency as a higher frequency content than the S wave. Okay, so P wave becomes more dominant, and in the other structures, in the horizontal earthquakes, S waves is more dominant. So your mode of action changes, and you know that P wave is the primary wave, and it comes fastest and acts faster to the structure. So if P waves are stronger, then your structure will be attacked faster, and it will create a damaging effect before the alarm is raised. Okay, so that is the reason this vertical earthquake is very serious to consider, and it tends to concentrate all its energy in narrow high frequency band, which leads to largest vertical to horizontal spectra ratios in short period range. In short period range, that is 0 to 0.3 second, it will have a severe effect on the structure. And for that, we should design the structure in near source region or zone 4 or 5 regions. And that is the reason this factors, scale factor that has been mentioned, and the multiplication factor will play a vital role in defining the function as well as the load case in the vertical earthquake case and combination with the horizontal cases. So three directional earthquake we should consider in seismic zone 4 and 5. In India or anywhere wherever the high seismic zones are there, this is what it should be considered. Okay, so surface wave, and there is epicenter. So you can say that this is the Rayleigh wave is happening like this, and uh, elliptical orbit of the ground particles. So this is how the Rayleigh wave is trying to damage the structures. So amplification and vibration of the axial force demand on the column. So S wave, P wave, and Rayleigh wave. So all will act on your structure in vertical earthquake condition. So amplification and variation of the axial force demands in the column will increase, right? So that is the amplification. And increase in girder and pier moment demand. So if you have a bridge, the pier and girder, the moment demand will increase, and in the buildings, the axial force demand on the column will increase. Reduction in the shear capacity of the section, Reduced energy dissipation capacity of the structural members and connections. So ductility is reduced because energy dissipation is reduced. So these are the effects of the vertical earthquake. So now you can see the bending moment diagram of vertical earthquake and the horizontal earthquake. So this is how the vertical earthquake looks like, and this is how the horizontal earthquake looks like. So that is the difference between the bending moment diagram. So what type of means which earthquakes had severe vertical component? So if you want to design a structure considering the vertical earthquake, then you should take all these time histories in which the vertical acceleration is of significant component. So Kobe earthquake, La Aquila earthquake, Chichi earthquake, Parnitha earthquake, then Aegean earthquake, Northridge, California. So all these earthquakes you should consider if you want to consider as time history for vertical earthquake condition. Yes, so they were very severe in vertical direction. Now, what is the problem with definition of the response spectrum? So here you can see 2 by 3. So this is what has been defined in the IS code. So this is what is 2 by 3, a flat graph, right? So a flat graph is shown, that is a 2 by 3 of the horizontal spectrum. Now what they say that this is not a representative of let's say uh, vertical to horizontal ratio. It is not a real representative. It is a overestimation. So it is a overestimation on one side, okay, and underestimation on the other side. So on one side it is overestimating the result, and on other side it is underestimating the results. So that is the reason that the Eurocode and any HERP code, they have defined two type of vertical earthquake response spectrum, type 1 and type 2, in which in high seismic zone they have defined this response spectrum, and in low seismic zone they have defined in this response spectrum. So in low seismic zone this is high, right? So this will be high if we are considering low seismic zone, and it is low if we are considering high seismic zone. So Eurocode type 1 is there, right? And this is type 2, high seismic and low seismic, and this is in between. So they are saying that if you are use a in between horizontal vertical response spectrum function, then in higher seismic region you will be considering less, and in low seismic region you will be considering more. So your particular type of function should be defined in a better way, and Eurocode and any HRP guidelines have defined it, considering also in America and in Europe, they have defined a different type of vertical response spectrum function, and in the other countries it is taken as 2 by 3 of the horizontal acceleration. So this is also one just information that I have provided you, that generally 2 by 3 is either overestimate or underestimate. So for a regular building, let us try to see where there are no overhangs, no cantilever in horizontal and vertical direction, no projection is there, a simple type of structure is there. So if we consider this as one sample and try to find the effect of vertical earthquake and horizontal earthquake and try to calculate it manually, then we will be able to find the difference. So I leave to you that how you manually do it or you do it in software, you will also get the results, but it is always better to create your Excel or do it with calculator. So this simple example, you can see what is the effect of vertical earthquake on the shear force and bending moment of columns and beams. That is type 1, example number 1 that you should test. This is example number 2, in which you can see very 10 meter. Okay, so this is 10 meter and this is 5 meter. So two type of two overhangs, two side overhang is there, in between large span is there. This is all 5 meter, a regular frame. Okay, this is again 10 meter and this is 20 meter. So these type of frames you should test without application of any load. So I have not, this is only dead load condition. So in dead load condition, what is the effect of the vertical earthquake that you should consider? and then you should try to realize that what is the effect of vertical earthquake. If there is a large overhang or there is a large span, then what type of oscillation or what type of time period in the structure is okay. These type of problems you should try by yourself. Different cases you can consider. You can also consider a vertical column of, let's say, 10 meter, then a vertical column of, let's say, 5 meter, and try to check what is the effect of vertical earthquake. And you provide different type of loads, that is 10 kilonewton to 100 kilonewton you can apply on these vertical columns, and you can check that what is the effect of vertical earthquake when the load is changing. So this is how you can try to do various type of studies and understand that what will be the effect of vertical earthquake, because it is through observation only you can understand the effect. So these models you can try by yourself, very simple to make and very fast it will complete. Only the effect you can see it by yourself. So this is one type of example in which there is a vertical projection on top and horizontal projection on bottom. So there is a porch and one story above, okay, on one side, and this is the vertical projection. So this building suppose is in zone 3, right? So I don't have to consider vertical earthquake, but still I have to design these vertical projection cantilevers and horizontal projection cantilevers for vertical earthquake condition, right? So if the building is in zone 3, still I have to consider these two parts, separate it out, and design for vertical earthquake. Okay, so this is what is one type of example you can also make for your building. So this is quite a high building that was made, and you can try with different type of examples. This is the again what is happening in this. You can see in this structure, diagonal bracings are provided. What happens that when you provide diagonal bracings or diagram type of structure, when the earthquake in vertical direction will occur, the axial force in these members will exceed, and if they exceed by a high amount, then this bracing is for 2 stories, so your capacity for 2 stories will reduce. So this is very serious. If we are not considering the vertical earthquake, then the severe failure in the building can take place. Similarly, for different type of buildings, what are the load cases for vertical and horizontal earthquake? Three-dimensional earthquake, design load cases combinations for three-dimensional earthquake. So 1.5 dead load, 1.5 dead load plus live load, earthquake in X 1.2 minus earthquake in X 1.2, earthquake in Y plus minus, then 1.5 dead load plus minus, 1.5 earthquake in Y plus minus, then again plus and minus X and Y. So these are X and Y conditions we have taken. Now for response spectrum function, this is for X and 0.3. So we have to take 30%, so 0.3 into 1.2. So it will be 1.2 into 0.3, it will be 0.36 into Y plus the vertical earthquake. So it becomes 0.36 for response spectrum X positive and response spectrum X negative. Okay. So here it is negative. Now 1.5 dead load plus response spectrum in X plus 0.45. So how it is 0.45? Because it is 1.5. 1.5 into 0.3 is 0.45. And 0.9. So this way it is right now defined for RSMX and RSMY. So right now I have just created 20 load cases, and similarly different load cases you need to create in your structure. So I will just show you that particular load case. So this I had created in ETABS software, and I have exported that into ETABS into Excel. And here, let me just click here to accrue below. So these are, I think, 4 to 100. I think 4 to 100, right? So 94 load cases are there that are defined in ETABS by me. Okay. So this Excel file I will send to you. You just see how the load cases are defined. These are for vertical earthquake, right? So it is clearly mentioned. This is earthquake X and Y. Again, it is vertical earthquake. So whenever you are designing for vertical earthquake, you can load this file in ETABS and you can run your analysis and you design for all these load cases without having any problem. So once you define it, every time you can do it by yourself. Okay, so this was the PPT. Okay, so anybody has a doubt in this, they can ask. And they can share their results if they have used for vertical earthquake. So Jan, you have a doubt?
I have none as of now, sir.
Okay, okay. And Subhash?
Sir, no, sir. I have to go through one more time.
Okay, so let's take a 2-minute break. So I will open the ETABS and then we will connect again. So we meet at let's say 8:10. So we'll meet at 8:10. Okay, so let us begin the session with a small example. And this is a simple building. I hope everyone has come back after a small 4-minute break. So this is a simple 7-story building, and the height of the building is 21. So it is around 22-meter height. The building height is 22 meter, and 7 stories are there. And it is a very simple plan. No projections vertical, no projections horizontal. So what we have to do, we have to first check what functions have been defined. So one function I have defined is zone 4, in which I is 1 and response reduction factor is 5. So this is the horizontal acceleration. So I will take it as unlock this model. Then I will define it as a horizontal acceleration. So this is AH. And this is the vertical response. And this is called AV. So this is AV. And here you can see for defining this response spectrum, I had converted it into user defined, and whatever the values were given here. So here I have this function, right? So I will take one response spectrum function, add a new function, and convert to user defined. Here option is given to you. So if I take it to zone 4 and I make it R is equals to 1 and response reduction factor is 5. So your Z is considered, and your R is considered, and I is considered, and it is already taking as Z by 2. Okay, so this is right now Z by 2. So Z by 2 is considered. Your R and I are also considered here in the response spectrum function. So what has been considered? Z by 2 and R by I. Clear? So that much has been considered in this response spectrum function. So what you can do, 2 by 3, you can multiply it here, right? Into 2 divided by 3. So 2 divided by 3, that is what we have to give. Formula. So it is not taking this formula. So that we can do it ourselves. So 2 by 3 is always 0.66, right? So or 0.67. So that either we can apply it here or we can make it a scale factor. So right now I am taking I is 1 and R is 5. Zone factor is given and Z by 2 is done. So only thing remains is 2 by 3. Right? So 2 by 3 is not defined here. So I will convert this into a user defined function. So when I convert it into a user defined function, what you can get is these values. So these values, what I will do, I will try to modify. So I will modify as 2.5, modify it. Again click, it is 2.5, modify it. So this you have to keep on doing it until you reach the last value. So that is the one way. Another way is you create an Excel sheet and you upload it here. So that is also user defined, you can create. So this is how for all the time periods up to 9.5 seconds what has been given. You can, so this will also happen fast. Just you click and type 2.5, so it will not take more than few minutes for you. Okay. So this is how this response spectrum function is defined as a user defined function. So all values are 2.5. So that is what you can see here, a flat curve of 2.5. This is okay, and 5% response spectrum function is there. So Z by 2, R by I, okay, that factor covered, and 2 by 3 is not there, and 2.5 SA by G. So this vertical response spectrum function, horizontal response spectrum function that has been defined. Okay, so this is okay. So two functions need to be defined for vertical earthquake, and your second thing is your mass source. So in mass source, dead load plus live load has been given, but previously we had not considered vertical mass. We have to consider vertical mass for vertical earthquake, otherwise it will not consider the vertical earthquake. So you have to tick this option to consider the vertical mass for vertical earthquake. So that is defined. Okay. Then what is required is your load cases. So in load cases, you can see model, right? So model eigenvalue is given, but for vertical earthquake, we require Ritz vector. We do not require a model vector. So what we have to define? We have to define a new case. In this, you give the model underscore Ritz. Okay. And in that, you have to take this as model. So your model in eigen, you have to select Ritz vector, right? So this is how you will define your function, and you will add it here. So this will be an acceleration in vertical direction, right? And means preset p delta that you don't have to consider. It will be considered here, and number of modes, it will depend upon your building. Okay. Hold on. Okay. So this is what was created. UZ and number of cycles is 0. Target dynamic participation mass ratio should be 99%. And currently 12 I have defined as the number of modes, so that is not a problem. Okay, so this is the Ritz vector model case that was created. And this delta preset setting is kept on here. So that is the Ritz vector for vertical earthquake, and this is for horizontal earthquake. So two model load cases you need to create: model eigen and model Ritz. So for your response spectrum X function, you have horizontal acceleration, you have defined it, you have given the eccentricity of 0.05, that is 5% eccentricity is there. Scale factor you have given here, so 9810 multiplied by your scaling of the base shear, static upon dynamic. So that scale factor is given here. Okay, so this is the scaled response spectrum that you are using for design of this building. And this is in Y direction, same scale response factor is given. So next, what you have to create a response spectrum function in the vertical direction. So response spectrum in vertical direction, define it as response spectrum. Acceleration, it is in the third direction, U3, and the function that you had defined of vertical acceleration, it is there. And here you can see the scale factor that was to be G, right? So now it is 339.03. So how it is 339.03? Why it is only this much? Can anybody tell based on the explanation done by me in the PPT? So your G value is 9806.5, right? So in vertical earthquake, it is 339.03. From where this value has come? So this is very critical. Without this definition, it is not correct to do. In the previous response spectrum function, I will take you back there. In this function of vertical earthquake, now you have seen that we had defined I, we had defined R, we had defined Z previously. Now we have deleted everything. Now everything is 2.5. So your Z by 2 and R by I now got eliminated here. So only SA by G is there, 2.5. Your function is only 2.5. So your scale factor of 2 by 3, Z by 2, R by I now needs to be defined in the load case for the vertical response spectrum. right? So this is Z2 by 3 into Z by 2 R by I, and that multiplied with multiplication factor. So this scale factor will come from that 339.03. So any doubt is there in this how it is obtained? 2 by 3 Z by 2 upon R by I multiplied by multiplication factor, that is scaling in X, scaling in Y, maximum whatever is obtained, this will become the scale factor. Any doubt? Okay, so moving ahead. So this is how the vertical response spectrum load case is defined. Okay. So these two things you need to define for vertical earthquake. Rest remains the same. Okay, so this is what you need to create for vertical earthquake. So this is done, and we go to load combinations now. So you can see all load combinations. I have called it here. Okay. So how it is called? So how to call it? Go to edit. In that there is one thing called interactive database. Okay, so this is interactive database. Now in interactive database, you have here load case definitions and load combinations, right? So load case definition, load combination. We are interested in load combinations. So what we will do? Expose all input tables. Okay, we have to click this expose all input tables. Load combination definitions, and we take it as okay. So right now this data is available. Okay, so what you can do once you have defined it here, so you convert it into Excel, send tables to Excel. Okay, so this table will be now becoming the Excel for you. Now you save this, and I call it vertical earthquake load combinations. I save it in the location wherever I want. Now it is done. Okay, so whenever you will open a new ETABS file, in that same you have to do. You don't have to define any load combinations. In load combinations, nothing to be defined in the new model. You go to edit interactive databases and open these combinations definition, export all input tables to make it okay. When this will open, it will be blank, right? So when it is blank, what you will do? You will say send Excel to table. Okay, so in that also you will send Excel to table, and this will be all blank, right? So when it will be all blank, just copy paste those Excel combinations here and close it. Automatically your load combinations will get transferred in your ETABS file. So retrieve table from Excel. You can see here, right? Retrieve table from Excel. So you have to click in the new model whenever you create a new model and you want to call these load combinations, retrieve table from Excel. So when you will click this retrieve table from Excel, it will ask for a location. You select that particular Excel and copy paste those load combinations here, and it will be created in your ETABS file. You try it, and if you have a problem, then in next session we will try to cover that. Okay, right now we will see what is the effect of the vertical earthquake, and we will now run the analysis. So I will first uh, first what I will do, I will go to analyze and I will not run the vertical earthquake. So I will keep it to do not run. Okay, so I will only run the horizontal earthquake. So all vertical earthquake response spectrum function will be 0. Okay, now we will see in the elevation, in the front elevation, that what is the bending moment for let's say response spectrum function x is there, y is there, and combination is there. Okay, so in this I will select 1.2 dead load plus live load plus earthquake in x, right? That I will select the particular load case and I will check the moment. So what is the highest moment is coming is 385 kilonewton into meter. So that is the highest moment. So just note it, it is 385 kilonewton into meter in the ground floor columns or 1.2 dead load plus earthquake in x direction. 385. Similarly, I will look for other load case in y direction. Okay, just we will check for the x direction and what is the shear and what is the axial force. So axial force is coming as 1659. So what I will note down that what is the force is. So moment is 385 and your axial force is 1659 kilonewton. And let us see what is the shear force. The shear force is 129.09. So I have noted these three values and I will again unlock this model and I will go to analyze, set load cases to 1. Now I will make it run. Okay. So now all load cases will run. So this way we can compare that what is the change in the bending moment, axial force and the shear force when the vertical earthquake is happening on a regular structure. And no projection is right now we have provided. So let us again go and check. So here it was 1.2 dead load plus live load response spectrum function is there and we require for earthquake X. Okay, so for earthquake in X, it remains the same. Okay. Now what we have done, the response spectrum function of 0.45 and there is 0.36. So dead load plus live load response spectrum in X plus 0.36 in Y plus vertical direction. So this is the 3-direction earthquake. That is what we are considering. So if it is a 3-direction earthquake, then it is 420. So this is the moment diagram. So from 385, the moment has become 420 kilonewton into meter. And your axial force has increased from 1659. It is now reduced. So from 1659 kilonewton, it has become 1536 kilonewton. So your axial force is reduced on the member. So your ductility will change for this column. Next is the shear force. Your shear force is 144. To 144.85. So from 129, the shear force is increased to 144.85. Okay, so much. What is happening? The shear force is increasing by around 20 kilonewton. The moment is increasing by 40 kilonewton to meter, and axial force is reducing by 100 kilonewton. So that is the change in the axial force, bending moment, and shear diagram. So shear force will increase on the ground story columns, and that is the reason the ground story columns are susceptible to the vertical earthquake. So this was about the vertical earthquake for the regular structure that is does not have a projection, and I will share the model with the projection with you. You can look at what is happening in those type of models, and then we can connect again and try to see what is happening in the other type of structures. So I think this session is understood, then it is very critical for the structure. So Mr. Vinod, can you let us know, in UAE, are you designing for vertical earthquake?
Yes, sir. We consider vertical earthquake, but we consider 2/3.
Yeah, so 2/3 is general criteria everybody is considering. So this is the way you define, right? Vertical earthquake.
Yes, sir. But scaling we make a different way. Only we scale with 2/3 of the maximum X and Y.
Okay, so you don't scale the base shear, right? For vertical earthquake. Scaling, you don't, multiplication factor you do not do.
Yes, sir.
So you apply a 2/3 and 2/3 of AH is the vertical earthquake, right?
Yes, sir. Same as X and Y, and also the you change that is 2.5.
Yeah.
That one we don't make.
Yeah, so means different codes have different requirement. Only thing is it is to be understood that what will have effect of vertical earthquake, and how it is to be defined in ETABS, and how to understand in what cases it shall be applied. So in what type of structures you consider vertical earthquake?
Here normally more than G+10 building considered
Okay.
vertical earthquake.
So in your region, what is the maximum earthquake expected?
Here, sir, 2.4 and 0.74, that is SSS1 value.
2 point?
0.4, sorry, 0.24.
Okay, okay.
0.248.
0.248 G.
Yes, sir. And
Okay, okay.
this is 1 second, and shorter one, 0.826.
Point
0.26. 0.826.
so this 0.826 is what?
So SS and S1. The 0.826 is the SS value
Okay.
and S1 value is 0.248. So near Z
Okay.
value near about 2.4.
Z value 2. Okay. Means what is the acceleration you consider? So this is your spectral acceleration value, right? So this is to be divided by G, or it is SA by G graph, or what it is?
No, sir. In ACI code there is formula, different formula. FA,
Yeah.
B. And
So they define generally the acceleration.
Yes, sir.
So
Before
as
we
per
use,
any
yes, sir. Before we use sir UBC code, and that time only we defined a Z value 0.2.
okay. Yeah, so as per any HRP guideline, I think it is mentioned that as per different zones, there is a different type of response spectrum function, and that is what you follow. Okay, so as per American code, it is correct. So for your 10 to more than 10-story building, you consider what?
The 10th story, and here the maximum buildings are vertical irregularity is there. Maximum building they use floating column.
Floating column, yes. So floating column, vertical excitation is very critical. So that is very much needed to consider the vertical earthquake.
Yes, sir.
So as per IS code, floating column is not allowed. So if you are providing a floating column, then you have to prove it is only a gravity load resisting system. So it is not taking any lateral force that you have to prove. Otherwise, you cannot provide a floating column.
Yes, sir.
So that is the change done in the IS code, because many structures fail due to floating column.
Yes, sir. But when it is designed, normally the bottom is released, moment is released, the column bottom is released by moment.
Yeah, so what happens is that you are providing that release, but it is actually happening or not. That is not known to anybody, right? So in maximum considered earthquake, will this act as a lateral load resisting system, or it will act as a gravity load resisting system? So if it is a gravity load resisting system, no problem. But if it is a lateral load resisting system, then you cannot release the moment.
Yes, sir.
So this is the problem. People make a model in which they release the moment, but it is in actual practice, it should not be released.
Yes,
Right. So that is why the IS code is not allowing to give the consider the floating column as lateral load resisting system. You cannot take it as that column that will take the lateral force. So lateral force is 0 on that column. It will take only the vertical gravity forces.
Yes, sir.
So I hope you can also improve on that if it is possible, because I don't know, in India also many people are still not following that. But floating column is very preferred in Mumbai, in Delhi. So they are all building will have a floating column.
Yes, sir.
Okay,
But
so
here actually from the previous there is a trend to use the floating column. So if someone not use, then the pressure come on him. Why not use floating column that engineer use and that is approved by the municipality?
yeah, so basically you should design. I don't say don't design, but you should see that it does not take the lateral force.
Yes, sir.
It can be provided, but it is only part of gravity load system. Okay, so that depends on your particular IS code does not allow. So we have a criteria as per the code that we cannot provide. If your criteria is not that way, then I don't know how you will be able to manage that. But at least try to convince people technically that this is wrong and it should not be provided. You can give the reference of the Indian code also, that in Indian code they have banned the use of floating column as lateral load resisting system. So if I provide, not a problem, but it will not act as a lateral force resisting system. Right. So that is
Yes.
what you can at least try to prove technically. If somebody agrees with that, then it is well and good. Your practice, they will appreciate more.
Yes, sir.
Okay, yeah. Jen, is it clear what is what we have done today?
Yes, sir. Yes, sir.
So I think Singapore is not earthquake sensitive, right? It
Yes,
is,
there's no seismicity here, sir.
yeah. So it is more of wind governing
Mm.
region.
Yes. But in the Philippines, it's seismic zone 2 and 4. So maybe I would be implementing this in the Philippines, projects in the Philippines.
Yeah, Philippine all type of hazard are there. It is most sensitive to all type of hazards.
Mm.
So
Yes.
that is where there it will be applicable to everybody.
Mm.
Okay. Okay. So just go through the session today. Try different examples, and we will meet on Monday. There is a steel design demo. So on Monday lecture will not be there. So we will be looking at the demo of a Strap 2021 and Vortex PD software. So that link I will share with you. And so we will meet on Wednesday or Thursday next week for the missing that lecture we miss on earthquake on Monday. We will take on either Wednesday or Thursday. Okay. Okay. So I will stop the
Okay, sir.
recording.